Okay, this is the end of Unit 3. We're going to continue talking about solutions and then light and instrumentation. When talking about how solutions form, remember IMFs do play a role in this. A solution, we said last time, consists of a solute dissolving in a solvent, and there has to be attraction between those components. Okay, so we can't just say like dissolves like, polar molecules dissolve in polar solvents. We have to describe the IMFs that are causing that attraction between the two different molecules. So as you see here in the question, this is just kind of a review, what IMF is represented in the solution. So we'll be talking about here after the solution is formed. Notice these are ions and that's water, so we would say ion dipole. Again, a little bit more of a review. This question, which vitamin is most soluble in water? And an AP question would say, explain your reasoning or explain your answer. So notice vitamin A has this long carbon chain of hydrogens, and then at the end we do see that OH attachment, which we've talked about as a site of hydrogen bonding. So that is where some hydrogen bonding could occur with water. But then we take a look at vitamin C and we notice, wow, there are 4 different OH sites. So which would be more soluble in water? Hopefully you would select vitamin C. It has many more areas where water could hydrogen bond with it, and therefore it definitely would be more soluble. Now on the formula sheet, molarity is defined as moles of solute per liter of solution. So just a reminder, you probably studied this in your first chemistry class. And you know, another detail, volume can be temperature dependent, so molarity could change with temperature. We don't see that brought up very often, but just as a reminder. Now when we're making solutions, you might have to, on an AP question, like describe how to make a different kind of solution. So I put up some samples of glassware that are most commonly used to make solutions. First of all, the volumetric flask is really required. A volumetric flask only measures, if you see that line that's kind of zoomed in on, a volumetric flask measures one volume very precisely. So if I needed to make, if you notice the label here says 1,000 milliliters, if I needed to make a liter of solution, I want to choose that size volumetric flask. Now, there are different ways, like if we're doing a dilution, we'll talk about in a moment, that we could put a smaller amount of a concentrated solution into a volumetric flask to make a larger volume of what will then be a dilute solution. So our first choice, if we're doing a dilution, we'd probably want to pipette a solution into the volumetric flask and then fill to the mark with water. A burette is a very precise measuring instrument as well. And then, you know, I would say those two probably be tied for their precision. And then our second choice would be a graduated cylinder. I know in our labs we tend to use graduated cylinders a lot, and they're great measuring instruments, much better than anything else that's not picture. We would never use a beaker or a Lamar flask or anything like that, but pipettes and burettes, if you're, hopefully you'll have some time to work with those as well, but those two are first, and we would go with graduated cylinder second. And significant figures, you know, are important because they come from measurements. So, you know, you might be asked, like you might be given something like this, a picture of a graduated cylinder or a burette, and asked what the volume is, or what is the amount of solution that was maybe delivered from a burette or something to that extent. And you have to be able to read the volume to the correct number of significant figures. Okay, so notice under here it says this is a burette, and we can tell it's a burette because notice the numbering is going up. As it goes down, the numbering goes up because it's the amount that you drain out of the burette. And remember, burette looks like this. The amount that you use out of the burette is the meniscus, okay? So when you read that volume, that's how much you've actually used if you started at the 0 mark. So notice that if we look at this really closely, at the bottom of the meniscus, we see it's a little bit past 24.7, and the next mark is 0.8. See, this tells me if I need another estimated digit to correctly say that what this exact volume is. That means I need to estimate that next digit, and all of us may not have the same number, and that's okay, and the AP exam understands that because it is an estimation. There are no other markings in between those tenth lines. So I might come up with 24.75, you might say 24.76. As long as we're close to the value that they're looking for, we would get credit. One thing I do want to say here, if the meniscus was exactly on 0.7, you also would still need an additional digit. So you would have to record it as 24.70 to say, hey, this wasn't, a little past the 0.7, it was exactly on that line. And then along with significant figures, when we make solutions, sometimes we'll take a solid and dissolve it in the volumetric flask to make a different kind of solution. And just remember your significant rules when you're subtracting. As you can see on this balance, the mass was 55.1345 grams, we would want to subtract out the mass of the container, which in this case was a beaker, and we would still need to make sure that we recorded our answer to 4 decimal places, even if the last digit was a 0. Don't drop that. Okay, so here's the dilution relationship. I tend to use this with my students. A lot of textbooks use C's and D's. It doesn't matter. Neither one is on the formula sheet. This is just a relationship you need to know. So either 1s and 2s or C's and D's, but whichever way you learned it or are learning it, just remember the 1s or the C's mean the concentrated solution, and then the other side of the relationship is going to be the diluted solution. So basically we'll have 3 of these 4 numbers and we'll solve for the 4th. And the difference in the volumes from V1 and V2 or VC and VD is how much water we're having to add to the volumetric flask and fill to the mark. So here's a picture of this solution, making this solution. And you can read this. If I took a 1 molar solution and pipetted 1 milliliter of it to make a new solution by adding 9 milliliters of water for a total of 10. So again, it's the new solution would be the total volume. What is the new molarity? So notice I just set this up. I divided by 10, and notice this is an example where volume, as long as these volume units are the same on both sides of the relationship, they can be in milliliters. If you want to change them to liters, you can. It's not necessary in this case. So notice when I divide by 10, I just get 0.10 for my molarity. You might be asked to explain how to make a solution. So again, this prompt kind of talks you through how the solution was made. I provided a picture so you could also see that. The key is you're going to fill to the mark. And again, if we're making 10 milliliters, we'd have a 10 milliliter volumetric flask, not a 500, but just that graphic's there just as an example. Here's another question. If you kept diluting the new solution, if I repeated the same procedure, pipetted 1 milliliter from that solution I just made, again I'd be making 10 milliliters total. Notice it's getting more diluted by a decimal place. So this is a tenth the molarity as the previous one. And by doing this, that's called a serial dilution. If we did the same process again, the next molarity would be 0.0010 molarity. Okay, now we're going to move on to the other way we can make solutions, and that's if we need to use a solid and dissolve it in water to make a solution. So first we talked about dilution, now using a solid. So notice reading through this information, if 1.25 liters of a 0.150 molar solution of potassium permanganate is needed, describe how the solution would be made, including any calculations and necessary lab equipment in your answer. Okay, so here's an example. Basically, we need to know some amount to put in our volumetric flask. We're going to add water. You'd be swirling while you're adding the water, and then eventually you're going to fill to that mark. So we would want a 1.25 liter volumetric flask, and they come in all different sizes. So first, the math. That's usually going to be the easiest thing. So if I have molarity and I already have liters, I need to think about my molarity relationship, because I've got to measure out a mass of a solid. So if I say molarity times volume in liters, that gives me moles, which is what I've done here. So that's moles of potassium permanganate. And if I need to go measure this on a balance, I can't measure moles. I need to add up the molar mass, which I've done here, multiply moles times molar mass, and that tells me I need to go to the balance and mass out 29.6 grams of KMnO4. So and again, here are the directions. This is just an example to help you see what this question would be looking for, because this would be a good AP question. So I'd mass that much out on a balance. I would place it in that specific volume that I've been told to make, volumetric flask, fill to the mark with distilled water while swirling. Okay, so that's just, or while mixing. So there's a good graphic of that as well. Okay, now we're going to kind of switch gears a little bit and go talk about light and the electromagnetic spectrum, and then at the end of this you'll see how solutions and this come together with Beer's law. So I know in your first year class you briefly talked about the electromagnetic spectrum. What we need to do is really, our focus is mainly on UV, visible, and IR. Okay, so how would we contrast these? Well, we could talk about them in terms of frequency and wavelength. So of these three, notice you've got UV, visible's in the middle, and then there's IR. What would we say about their frequency? Okay, so if you look at the scale on the left, you can see that UV light has the highest frequency, visible in the middle, and IR has the lowest. And how does that correspond to wavelength? So things that have high frequencies have the, if you notice, those are the smallest wavelengths. So that's a connection we need to make, that high frequency waves of light have very small wavelengths. And this is that inverse relationship that we just said. So wavelength has the symbol lambda. When we do calculations, the units do need to be in meters, but when we're talking about light in chemistry, typically, we are giving wavelength in nanometers. So remember, 1 meter is a billion nanometers. Just a quick review of that relationship. So you would need to change, before you can do any calculations, you need to change the nanometers to meters. Then we have frequency, has the Greek letter nu, and the units are hertz, but really all hertz is cycles per second. So 1 over seconds. The AP exam likes to take a denominator, and I think it's just because it's easier to type. They'll use seconds and raise it to the -1 power instead of writing 1 over seconds. I prefer this version. I like things that are in the denominator to look like denominators. If you prefer these -1 exponents, that is totally up to you. You're not required to write units that way. So, on the formula sheet, this is on the very front of the sheet at the top, you'll see this, I call it the speed of light formula. Okay, here's the question. What is the frequency of violet light with a wavelength, and there's our nanometers, of 400 nanometers. So as I said, we can't use nanometers, so we know we're going to have to make that conversion. Okay, and if you see, they've done that right there. Now, C is speed of light. We know wavelength and frequency. What we need to be reminded of is, first of all, C is given on the formula sheet. All forms of electromagnetic radiation are going to travel at the same speed in a vacuum, and so here's the exact value given, 2.998 times 10 to the 8th meters per second. So basically, we just need to rearrange to solve for frequency. We've got speed of light divided by wavelength in meters, and you see why that's important, because we need our meters to cancel with our speed of light meters, and we're left with hertz. You could write hertz, or it could be 1 over seconds, or seconds to the -1 power. And then the other formula that's related to this is energy. Like, if we know any type of electromagnetic radiation, any one photon of any type of electromagnetic radiation has a certain energy associated with it. H is Planck's constant. This formula and the constant's value for Planck's constant are contained on the formula sheet, so nothing you would ever worry about memorizing. So in this question, it says calculate the energy in joules of a photon of blue light whose wavelength is 450 nanometers. So notice we really have to take into account several relationships. Okay, if we're given wavelength, first we need to think about the nanometers. That's not going to work. So notice that's what I did first. I divided by 1,000,000,000 to get my nanometers to meters. And then I can't, I could combine these two formulas to make one and solve for energy in one step. But, these are the two formulas on the formula sheet, so I'm going to use them just as they're written and just rearrange this. So I rearranged the speed of light formula to solve for frequency, because frequency is the connection to energy. Divided, I have my frequency, and then I multiplied. Here's Planck's constant, 6.626 times 10 to the -34th power, joules times seconds. Multiplied that times frequency. Notice my seconds cancel, and I'm left with my unit of joules with my correct numerical answer. So when we talk about visible light, you've heard of RGB, so that's what we call the continuous spectrum. It's all the different colors in the visible spectrum. When we have a element, what scientists have discovered is that we can identify elements by their emission line spectrum. So what happens is they take the element, they heat it up, so it's a gas. They run some electricity. Well, usually it involves some electricity. Let me just go to this page. Notice they've got this hydrogen gas. It's energized. Then it goes through a lens, a slit, a prism, and if you see these 4 bands of color, you know that this is hydrogen. So elements have these specific wavelengths of light that are associated with them. So where is this coming from? Well, what happens is when the electrons are excited, they move to a higher energy level, and then they drop down to a lower energy level. In the process, they have to give off that extra energy as light in the form of a photon. Okay, so you don't really have to understand all of this. The key to this is, if electrons gain energy, they move to a higher energy level, and when they drop down to their what we call ground state, which is their lower energy level, they give off energy, light, in the form of a photon. So you can see all of this is to say that elements, we can tell which elements are present using this, and it just explains that this connection of of where electrons are located and the excitement of electrons and then moving to a ground state. There are types of spectroscopy that you could be asked about. If you think back to Unit 1, we talked about PES, which is another type of spectroscopy. It has to do with photo-electron spectroscopy, and that's where energy was added to atoms, and the electrons became so excited they didn't just move to a higher energy level, they actually left the atom. And that's how we were able to see, how much energy it took to remove those electrons. We could tell their electron configurations. Those were related to ionization energies. So these other three types on this slide are just a continuation of that. And of these three listed, the one that we would be able to do a lab at school would be UV Vis Spectroscopy. Sometimes schools might have a spectrophotometer, or we might get one from Science in Motion. More times a colorimeter. It's just a simpler piece of equipment. They really do the same thing. Colorimeters only measure a few wavelengths of light, and a spectrophotometer you can measure, all the different wavelengths within usually the visible spectrum. But basically what happens is energy is added, the electrons, valence electrons are excited, and we can tell, and this is where we use Beer's law, we can tell how much energy or how much light is absorbed by a solution. So this is how we're going to determine the concentration in a solution. So that's what we're going to be using here with Beer's law. IR and microwave spectroscopy, as it says at the bottom, you only really need to know these minor details. You might have one question on the AP exam. We unfortunately would not be able to do this at school. So IR spectroscopy vibrates bonds in a molecule, so we could tell types of bonds. Functional groups might be like if we mentioned OH groups and other attachments to a carbon compound. For microwave, this rotates molecules and atoms, especially for polar molecules. That's kind of a key, so we can detail a structure. For UV Vis spectroscopy, this just kind of goes through hopefully what you'll do in the lab, but light of a certain wavelength is shined through a colored solution, so that's the key. The solution has to have a color, like over here you see it's fuchsia. The darker the solution, the more light it absorbs and the more concentrated it is. Okay, so that's a direct relationship right there. The key is to choose a wavelength of maximum absorbance. So if we have a fuchsia dye, we want a wavelength of light that absorbs really well. So then if we barely change the concentration of the solution, the absorbance will also change. So notice here is where this fuchsia dye absorbed well, and if that wavelength that represents that peak typically will be a complementary color. So earlier I mentioned serial dilutions. If we do serial dilutions of any solution that has a color, we can put those different concentrations of solutions in one of these instruments and read the absorbance value and then plot this graph. Okay? Because if we've done our dilutions correctly, what we'll find is that we have this linear relationship since it's a direct relationship. So then we could take an unknown concentration and put it in the colorimeter, find the absorbance of that, see where it fell on the line, and know what the concentration was. So again, absorbance of light is directly related to concentration. And this is called Beer's law. Absorbance and concentration are directly related. The other two parts of this, which is molar absorptivity constant and the path length, these are constants and they really don't change. So, and the path length is how far the light's traveling. It's typically a centimeter. You're going to use a square little test tube. It's called a cuvette. This is what you fill with the solution and put into the colorimeter. So here's just an example problem. So it says, what is the molarity of an unknown solution of copper 2 plus whose absorbance is 0.6? So we find 0.6, see where it falls in the line, and then we could answer the question. It helps to draw a straight line. Okay, I included a free response. The answers are included so that you can kind of test yourself, see how you did, and make sure you're understanding this last information from Unit 3.